We're on to the last lecture for a series on hydrocarbons on the energy transition. Last class I talked about solar, nuclear, hydro, wind, and one of the themes in those was copper plus rare earth elements. And these two things, this metal and this group of elements, which actually I'm going to write out for you here, rare earth elements, are used in generators. They're used to make magnets, generators. They're used to make magnets, they're used to make wires, to allow electrons to be made to move and then carry those electrons. So they're critical for electricity. And so what I would like to do today is go through 3 metals and the 17 rare earth elements. And that's going to be today's lecture, maybe a 10-minute. Let's see how it goes. This energy transition, while it has huge benefits potentially for the economy, for climate, maybe even for pollution, it still does require minerals. And minerals require mining, and mining has problems associated with it. And so there are some of the benefits to the energy transition that are going to be offset by problems associated with mining the materials to make things that are required for the energy transition. Right? There's going to be pollution. There's even going to be petroleum required in order to drive the big trucks and tractors, in order to mine these other things out of the ground. So with that being said, let us jump in to, oh yeah, we could put a heading in here. The heading is 3 metals and 17 rare earth elements. We're not actually going to go through all 17. We're going to keep it as a family, but I thought that was a cute way to say it. All right, so copper is the first in our list. Copper is a chemical formula of Cu. So I'll write down Cu throughout the lecture today, and it is required for wiring plus generators. It's a critical metal, so valuable and so important in so many different ways. The geology of copper has to do with magma chambers. And so let's say here is a volcano. And the volcano's erupting just to make it dynamic. And below the there's a magma chamber. And in this area, at the top of a magma chamber, copper gets enriched in certain environments. So we're going to say Cu enriched. We call this area at the top of a magma chamber a copper porphyry. Porphyry. And a porphyry, in my mind, sometimes means like a mixture. And the copper porphyry here is a mixture that has some copper in it, but the copper is actually not very enriched often. Sometimes it's just only about 1% of a copper porphyry is copper, but that's economically significant enough that we're going to mine it. The type of volcano is one that's called an arc magma, or a volcano that forms along a volcanic arc. Volcanic arcs are associated with a tectonic feature called a subduction zone. We're going to get to talking about subduction zones later in the semester. You've heard about subduction zones in other ways, though, because this is called the Ring of Fire. So the coast of South America, Japan, Alaska, Mount St. Helens, these are all volcanoes along the Ring of Fire. And we think in those modern systems, there is copper being enriched at the top of the magma chamber. But of course, that doesn't help us for mining copper, because we can't mine near an active volcano. So we need to go to the ancient ones. And so we mine copper at ancient subduction zone arc magma volcanoes that have now, because of erosion, ancient ones near the surface. They've been brought up to the Earth's surface. These get mined in incredibly huge, I'll show you one here from the western United States. I think this one's here in Utah. And for scale, I don't know, like there's a road, here's maybe a truck. These are big pits that get dug into the ground, and 1% of this huge volume that gets removed might be copper. And that is critical for our economy. All right, the second to talk about is a metal, one of the lightest metals, and it is lithium. And lithium is almost always talked about in conjunction with the third, and that is cobalt. And the reason why is lithium and cobalt are required for batteries. These are related to one another and how we're using them for the energy transition. We should go over each of them, but we'll do that in this space of the notes. I'm going to draw a battery here first. We're going to talk about how lithium and cobalt are used inside of a battery in conjunction. So with any battery, there is a positive end and there is a negative end. The positive end is called a cathode. The negative end is called an anode. And when we use a battery, we need electrons to go from the cathode to the anode, right? They're going to travel between these two. And if they're traveling, did I not forget to write down? I think I did. Anyways, when they're traveling towards the anode, maybe we are using the battery. And if they're traveling towards the cathode, they are recharging the battery. And so this energy can be stored and then used if we have cobalt and lithium. And the way that these two metals are used is that cobalt is used, how do we write this? We could go, so cobalt's chemical formula is CO and lithium's is Li. And so cobalt is used over here in the cathode. And the reason why for that is because it has a really high energy density. It has a really good thermal stability. So if you want to have a battery that charges fast and that holds good amounts of electricity and doesn't set things on fire, which is important, you might want it to have some good cobalt. And then lithium is used in a variety of different ways, but lithium is used in this gel, which is sometimes called an electrolyte, that sits in the middle. And these are not just normal lithiums, these are lithium ions. And so that's why these are called lithium ion batteries. And they are able to move in this direction or that direction. And what they do is they balance the electrons. So we could say something like lithium balances electrons. So if the electrons are moving in this direction, then the lithium is going to move in the opposite direction to keep the charge balance. The other place where lithium is used is in the anode, where it is sitting here bonded to carbon, and that has the negative charge. These lithium ion batteries, I put a picture of one in here just to show you. We don't tend to see them right at the bottom of a Tesla car or in some battery pack associated with a computer. But look at that. They actually look like little AA batteries, but there's just a lot of them stacked together. And inside a single one of these, this is the picture that I'd like you to have. All right. That's the engineering, the material science. That is not the geology, which is what I'm paid to do. And so the geology of lithium can be found in many different ways. And let's just list them out here right now. One of the places where you can find lithium is in minerals. And so we could say lithium-rich igneous minerals. Igneous means that they've crystallized from a magma chamber. And there are some places in the world where you can get crystals as big as a car that are 30% lithium. This is a mineral called spodumene. There's a place in Australia, there's a place in the state of Maine, where lithium is mined from spodumene. But it's not the most economically important source. There's another source, which is lithium-rich sediments. And this is oftentimes lake sediments, like clays, and these clays have bound to them something like, let's say 100 ppm, parts per million lithium. And if you were to just scoop up in a dump truck after dump truck after dump truck of 100 ppm lithium, you can process that and maybe turn a profit, depending on what the price of lithium is any given day. It's very volatile right now. The most important source, though, is lithium-rich groundwater. Sometimes these are called brines because it's not groundwater that you can drink. They're enriched in salt, they're enriched in other nasties, and they're also enriched in lithium. And so what people do when you have lithium-enriched groundwater is you pump that lithium-rich groundwater out of the subsurface, then you evaporate it in big storage tanks. And when you evaporate the water, you get left behind a powder that's rich in lithium, and then you will harvest that powder. Powder harvested. And this is the key, I think, to the future. We could circle this, we could star this. We could do that, let's just do it. There we go. This, I think, is the key towards our lithium-ion battery future. Now, how's cobalt used? All right, cobalt, oh boy, cobalt's a tricky one, because cobalt is only coming from essentially one place in the world, and it is the geology in an area of the Congo, which is an area, it's a developing nation in Africa. And in this one place in the Congo, where like 90% of all cobalt is mined, there is a manganese. All right, so manganese, that's not cobalt, something different, but it's a manganese ore deposit. The manganese itself could be worth some money, but in that manganese ore deposit, there's also been cobalt enrichment. And this ore deposit has been altered and weathered. It looks all rusted and crappy, and it's that alteration and weathering, weathered deposit that has actually created cobalt-bearing minerals that are in high enough concentration to actually produce with significant profit. Let me show you a picture from one of these mines. And this is getting a lot of negative press. So here, it's these green minerals here in this picture that you can see. Also notice that that rock that's hosting the green minerals that are rich in cobalt is just, it's either black or rusted looking. That's showing you this alteration of the initial ore deposit. But that's great because it has enriched the cobalt. But look at the mine. This mine is not modernized, right? This could be a mine from 500 years ago where people are going down of all sorts of ages, sometimes very young children are coming down here with pickaxes and shovels, filling the ore into bags, and then manually carrying it out. And so there's been a lot of negative press on Apple and Tesla and all these different companies that are relying on this kind of labor to produce their billions in profit. And I'm not here to speak about that. I'm not a pastor or a politician, but it's something that you as my students need to know that is associated with this, that people are working to fix, right? But it's a tricky subject. I guess what we could say here is that there is both environmental and human rights concerns. Let's say that. Concerns associated with the mining of cobalt, which is required for these batteries. Oh, I forgot to put in a picture of the lithium. Let me throw that in before we keep going. So if it's lithium-rich groundwaters that get pumped out, I got a good picture of that. Oh boy. That's kind of a messy insert by me. Here we are, mountains in the background, but we can see these tanks. These different colored, beautiful tanks are tanks of groundwater that have been pumped out, and they're at different stages of evaporation, where the different shade of blue or white is probably like heavily evaporated and nearing harvest, where these darker blue ones have just been pumped out. This is what I want you to picture, is where your lithium is coming from for your batteries. And now to wrap up today's lecture, we're going to go through the 17 rare earths. 17 rare earth elements. Maybe you have had high school chemistry and you've had to memorize the rare earth elements. They're an important batch. They're grouped. And they're grouped because they show similar characteristics. And so the rare earth elements are going to be these. So scandium, yttrium, lutetium, and then this group right here that sits down here on the bottom of the periodic table, from lanthanum to ytterbium. Those are your rare earth elements. The most important of them all in today's economy is neodymium. Now, of course, somebody could be offended by that because some of these others matter as well. But I'm going to put the eggs in the basket of neodymium is the one that most of us have in our pockets, or our electricity that we're using has been generated from it. All right, so the rare earth elements, we're going to say it's a family of 17 related elements. And the reason they're related based on their properties, they're all 3+. They all have a similar atomic radius, and that means that they can bond in similar ways, and they can be found in similar minerals. So when you find one, you often find more. The other thing about them that's similar is that they all are heat resistant, and they all share magnetic properties. And it is this magnetic property coupled with heat resistance that allows them to be used to make generators, magnets, and batteries. And so we could say something like it's these properties that lead to their ability to be used for, we'll go batteries, let's say magnets, and the magnets are used in generators, but also things like computer screens and cell phone screens, and of course also various types of weaponry. The geology of the rare earth elements is both simple and complicated. What's pretty wild about them is they're 200 times more common than gold. Right? Remember, uranium was more common than gold as well, and more common than gold. But gold concentrates in some really simple ways that allow us to find economically valuable deposits of gold more readily than we can actually find of rare earth elements. They tend to occur everywhere. In almost any rock you pick up, there are rare earth elements, but they are rare in Earth. And so when they are occurring at their background rate, we're talking about like 10 ppm, maybe to ppb, parts per billion to parts per million concentrations, unless they are enriched by some special process. And it's these special processes that geologists are going out and trying to find and mine. The number one thing you look for when you're trying to find an enriched deposit of rare earth elements is you're going to look for thorium or uranium, because thorium and uranium also share some similar properties, and minerals that have thorium and uranium also contain rare earth elements often. Now there's a problem with that. Thorium and uranium are radioactive. And so if you're mining a deposit of something that is radioactive, then your wastes are radioactive. And so there are environmental concerns with mining these rare earth elements because of this radioactivity. Plus, anytime you mine a metal, you are producing waste that is environmentally poisonous. The geologic systems that do get enriched in thorium and uranium, and also rare earth elements, they can be magmatic. All right, so certain types of magmas, magmatic systems, they're not the common ones. They're not arc magmas. They're not the magmas at Yellowstone. It's weird things you've never heard of. So let's just say this. Let's go magmatic systems with unusual compositions. Now I study magmas for a living, so I was about to talk about this too much. I was going to talk about carbonatites and peralkaline magmas, but that's like above even what majors might even study. So let's not talk about carbonatites and peralkaline, but if you could know they're from magmas with unusual compositions, that's a good thing to learn. Another place where you can find a lot of rare earth elements is in weathered clays. So these deposits of weathered clays above granite. And the granite has thorium, uranium, and the rare earth elements inside of it. And then as that granite weathers away, we can get this enrichment of the rare earth elements being left behind, and they get hosted in the clay. And then the last place where people are mining is coal deposits, because what we've found is that rare earth elements can be enriched in coal. And then we can actually go back to not to ancient, but let's say coal deposits from 100 years ago, and the stuff that's been burned from coal that's just pollution, we can actually go back to it, reprocess it now, and extract something we need for our economy from something that used to be waste. Now the last thing to talk about here with rare earth elements is just going to be the politics of it all. Of course, there's politics with anything that's worth money, and of course, there's politics with anything that makes pollution. But the politics right now, in terms of what the United States Geological Survey is working on, is something called strategic resource, where we want to reduce our reliance on foreign powers and other countries. We want to find more of it within our own country. So I would like you to know that rare earth elements are a focus right now for the United States Geological Survey, the USGS. We're going to say this is a USGS focus for discovery. There's a lot of money in this right now for young geologists who are coming through the system to get jobs, because we want to reduce reliance on imports from foreign countries. Because those foreign powers, they could shut us off and not allow us to have what we need, right? And so they could use it as leverage, right? They could use it as leverage in a time of war or some kind of economic dispute. So we could say that these are used as leverage, and it's not just in times of war. It could just be in time where we're trying to get our own way, or they're trying to get their own way with us for some economic reason. And so for this reason, the United States has termed these as a strategic resource, as well as a critical mineral.